Hey there, and welcome. Have you ever just stopped and wondered how your computer actually understands the code you write? Well, today, we're going to gently pull back the curtain on the process that makes it all work. It's called parsing. We'll be looking at a specific kind known as simple LR parsing. Now, I know, it sounds a little technical, but trust me, it's a really fascinating puzzle that sits right at the heart of how pretty much all software works.
Okay, so let's just start with something simple. When you and I look at a line of code like this, our brains, they just instantly get it. We see a variable x, we see it's being assigned a value, and we see a simple addition. But a computer? A computer just sees a long string of individual characters. X, then a space, an equals sign, another space, the number 2, and so on. So how does it get from that meaningless jumble of text to understanding the actual instruction? That is the big question.
And this isn't just some abstract theory I cooked up. The ideas we're talking about come straight from one of the most important books in all of computer science. It's often called the Dragon Book. This is literally the textbook that generations of programmers and computer scientists have used to learn how to build the very tools that run our modern world.
So the very first thing a compiler does is group all those individual characters into meaningful chunks. We call these tokens. So X becomes an identifier token. The equal sign becomes an assignment token. 2 becomes a number token. But that's just the first step. The real magic, and honestly the real challenge, is understanding the grammar, figuring out how all these tokens are supposed to fit together to make sense. And that whole process, that's what we call parsing.
You can almost think of the parser as being like a detective. It's got all the clues, those are the tokens, but its job is to piece them all together to figure out the underlying story, the hidden structure of the code. It needs to figure out that 2 plus 3 is its own little phrase, and that the result of that phrase is supposed to be assigned to X.
Now, there are a few ways a parser can do this detective work. We're going to focus on one particular strategy called bottom-up parsing, and it's actually pretty intuitive when you think about it. Instead of trying to guess the whole structure from the start, it starts from the bottom. It finds the smallest complete phrases first, and then it gradually builds them up into bigger and bigger structures, until finally, it understands the whole line. To pull this off, the bottom-up parser plays a very, very simple game. It only has 2 moves it's allowed to make as it reads your code. Just 2. These moves are called shift and reduce. Pretty much everything the parser does just comes down to deciding which of these 2 moves it should make next.
So the first move is shift. You can think of this as the gathering evidence phase. The parser just takes the next token from your code and pushes it onto a little temporary workspace, a stack. It's basically saying, okay, I see this piece, I'm going to hang on to it for a second and see what comes next.
And the second move? That's reduce. This is the big, aha, I see a pattern moment. When the parser looks at the tokens it's collected on its stack, and it recognizes a complete grammatical phrase, like seeing 2 plus 3 and knowing that's an expression, it reduces them. It replaces that whole sequence of tokens with a single, higher-level symbol that represents the phrase it just found.
Now this complete phrase that the parser is always on the lookout for, it has a formal name. It's called a handle. A handle is just that specific pattern of tokens at the top of the stack that perfectly matches one of our grammar rules and is all ready to be reduced. So finding the next handle is really the main job of a bottom-up parser.
Okay, so this all leads to a really big question, right? How does the parser know when to shift and when to reduce? It can't just be guessing. Well, it's not. It has a guide, a set of instructions. And that guide is this pre-built thing called a parsing table. For an SLR parser, this is its ultimate cheat sheet. And here you can see the whole setup in action. The LR parser has its input code, a stack where it keeps track of things, and that all-important parsing table. The whole program is just this simple machine. It looks at the state it's in, it peeks at the next piece of code, it consults the table, and it just does whatever the table tells it to do.
And the table itself, it's really not that complicated. It's just a grid. The rows are the parser's current state, and the columns are the next possible thing it might see in the code. You just find the box where your current state and the next token meet, and it tells you exactly what to do. So if the parser is in state 0 and it sees an id token, the table says, shift to state 5. That's it. It's an incredibly simple and really, really efficient lookup.
So if you boil it all down, the decision-making logic is actually beautiful in its simplicity. When should you shift? You shift when you're still in the middle of building a phrase. You need more pieces to finish the puzzle. And when do you reduce? You reduce the moment you found a complete phrase, a handle.
It's time to say, I recognize this, and simplify.
So why do we call it simple LR? What's the S for? Well, it comes from the simplified rule it uses to decide if a reduction is actually okay to do. When it thinks it sees a handle, it takes a quick peek at the next token in the input. If that token is something that's legally allowed to follow the phrase it's about to create, then the reduction is good to go. It's just a simple but really powerful look-ahead check.
So this whole elegant algorithm is really just this one simple loop, running over and over and over. First, look at your state. Second, look at the next input. Third, check the table. And fourth, do what it says. You just repeat this little dance until you've either successfully understood the entire input or the table tells you there's an error.
So why does any of this really matter? It's pretty easy to look at this and think it's just a neat academic puzzle. But this table-driven logic, it's so much more than that. It is the crucial bridge that connects the abstract theory of language and grammar to the practical reality of building software that can actually understand us.
And these LR parsers are everywhere for a few key reasons. First, they can understand a huge range of grammars, covering pretty much any construct you'd find in a modern programming language. Second, they're incredibly fast and efficient. They only need to read through the code once. And finally, they're great at finding mistakes. They can flag a syntax error the very instant things go wrong.
So, the most important thing to take away from all this is that this simple loop, check state, check input, consult table, is the quiet, invisible engine that's humming away inside the tools you use every single day. It's what lets your code editor highlight a mistake the second you type it. It's how a spreadsheet understands a formula you enter. It's a truly fundamental piece of technology.
So maybe the next time you write a line of code and it just works, you can take a moment to appreciate the quiet, elegant process happening underneath it all. Behind every app that feels seamless, there's this simple set of rules, patiently making sense of our instructions, one little token at a time. Thanks so much for joining me today.